as you heard, I'm going to talk about climate and energy in California. And I want to mention this is work, of course, done in association with my colleagues here at Scripps, Tim Barnett, Eric Alfaro, and Alexander Gershonov. We're all in the Climate Research Division here at Scripps. Well, I want to start, I'm going to take a moment to start and tell you how we got started in this topic, because I think how we got started is actually fairly interesting, and I hope you find it interesting too. This plot is a typical result you see for how climate might change in the future. What it shows is globally averaged surface temperature on the Earth from 1850 to the year 2100. And what you see is all these different lines here are different climate models, okay? And they show what these particular climate models expect might happen for the future climate of the Earth. And here are the climate models. It doesn't really matter what they are, but there's a bunch of them. One's by the Australians, one's by the British, one's by the US community. And the point here is we looked at this kind of graph and we said, you know, what does that mean for us? I mean, this is awfully abstract. We're just looking at globally average temperature. You know, let's say it does increase 2 degrees centigrade. Well, what difference does that make to us here in San Diego? Is that a big difference or a little difference? We wanted to know. So what we did was we took results like this and we applied them to our particular area. And then we looked at how they affected energy. So that's what I'm going to talk to you about today. And I want to point out before I start that the actual model we used, so right, we wanted to look at what this meant to us specifically. And before I go on, I want to point out the model we used was called PCM. And this is the temperature increase that PCM predicts. And if you look, you see that's actually one of the coolest, one of the least temperature increase models for these ones that you see here. So in some sense, these are very conservative projections. We did that deliberately because we wanted to have, we didn't want to just have a Chicken Little episode where we said the sky was falling. We wanted to be fairly conservative in what we were doing. So we decided to look at the effect of climate change in the western United States. And the reasons, besides the fact that we live here, so of course it was of great interest to us, is it's a very large and growing population in the US West, and it's a semi-arid region to begin with. So we wanted to look at how it would impact water resources. You know, we already have problems with water. I'm sure you've all followed the news about these, you know, it's a very contentious issue, transferring water between farmers in the Imperial Valley versus San Diego. So we wanted to see how that might change in the future. So we decided to use an end-to-end approach, and I'm going to tell you what I mean by that. Here's an overview of our project looking at how the climate might change in the future in the West. It had 3 parts. Now the first part was we initialized our climate change model with what's currently happening today. Our reasoning was that if you want to make the best possible predictions for the future, you have to start with the best possible estimate of what's happening right now. This was actually new work. I don't think this had been done before, interestingly enough. I'll tell you a little bit more about that in a sec. Once we did that, we ran the model forward for 100 years using estimates of what carbon dioxide would come out of, you know, factories and automobile tailpipes and that sort of thing. That part is fairly standard, so this part wasn't new. But then another new thing we did was we took those results, which were for the whole globe, and like I said, we wanted to see how it affected us here in San Diego or in the US West more generally. So we downscaled those results, and you won't be able to read those figures from there, but I'll give you much better views in a minute. But basically, we focused on the results in the US West to see what kind of changes would happen there. So the first step of all that was to begin with the current state of what the oceans show right now, today. And well, why do we do that? Well, I find it interesting that a lot of people don't realize that, but you've all read in the paper, I'm sure, about how it's been observed that the climate is warmer now than it was 50 years ago. Well, it turns out most of that heat has gone into warming the oceans. So in fact, about 90% of the heating over the past 50 years has gone to make the oceans warmer. You know, we live here in the atmosphere, at least that's what we really notice. So we care about this 3%. But if you're trying to do the whole globe accurately, you really have to focus on what's happening in the ocean. That's where most of the heat is. This shows pictures of how the various ocean basins warm over time. And it's fairly interesting that the different basins behave differently. So here's a little schematic of the world. We live here off the North Pacific. This picture shows how the warming happens in the North Pacific. So the axis here shows it starts in 1900 and it goes to the year 2000. And this is from the surface up to about 2 kilometers depth, which is a few thousand feet in the ocean. And what's showing is that over time, it's not that the whole ocean sort of gradually heats up and it's uniform and it's all very well mixed or anything. That's not the case. Instead, you see that it's trapped near the surface. That's because it's actually fairly difficult for water near the surface of the ocean to get down to the depths. So the heating gets trapped near the surface. Now, another interesting thing is, you notice not all the basins look alike. So for example, here's the North Pacific near where we live. Check out the South Atlantic. You can see there's much more of a tendency for the heating to be carried to depth. Now, the reason that happens is because the surface water there is very cold and dense. So it's much easier for that cold, dense water to convect to very deep in the oceans, in some cases quite near the bottom. So you get a very different heating profile depending on what ocean you're looking at, what sea you're looking at. And this was interesting for us because one of the things we did was, was compare this to how numerical models of climate change predict that the oceans should change. And we found fairly good agreement, which is nice because not only does 90% of the heating go into the oceans, but you can see it varies, of course, by what sea you're looking at. So the second step was to estimate the climate change that was due to the emissions of these carbon dioxide, greenhouse gases, and sulfate aerosols. So I'll just tell you a few words about the climate change simulations we did. It turns out the model we happened to use was called the Parallel Climate Model, PCM. I showed you a graph before that's one of the least sensitive of the world climate change models. So these are fairly conservative estimates. And this was made by the US community here, mostly in Colorado at NCAR. The scenario we picked, you have to figure out what's going to happen in the future for emissions of carbon dioxide. We don't know right now what's going to happen. Well, the scenario we chose is just called the business as usual scenario. That's the one where you say there aren't going to be any major changes. We're just going to kind of do what we're doing now. So then we'll see what happens under that set of circumstances. The period we covered was 1995 to the year 2100. And I find this fairly interesting. We did 5 ensemble members. What that means is we had this climate projection from a model, and we ran it 5 separate times. What we did was we perturbed a little bit the initial starting conditions. So we had 5 different examples of this climate. And the reason that's interesting is because any particular climate, like even on the real Earth, if you changed it a little bit, if you had 2 Earths and they were slightly different, in 100 years, they might have somewhat different climates because the climate's fairly sensitive to exactly these starting conditions. So when you do a numerical model, you have to take that into account. The way people do that is they do multiple realizations. In this case, we did 5. And then you see how different it is between the different realizations. And then you can average them to get the average effect. Well, one thing we spend a lot of time doing in the Climate Research Division, which, however, isn't tremendously interesting, probably to an audience like you, is validating these models. I mean, the way I like to think of it as you know, engineers use computer models to design airplanes. So you get in an airplane and you fly to Singapore, say, and you're not too worried about it because that airplane's been well validated through test flights and so on. Well, we do a similar thing. What we do is we take a model and we validate it by comparing it to what actually happens on the Earth. Now, like I said, we spend a lot of time doing that, but I'm not going to bore you with all the details. I'm just going to show you one illustrative example. This happens to be precipitation, so rainfall plus snowfall. That happens over winter, December, January, and February. The left-hand panel shows what the model predicts, and the right-hand panel shows what's observed. And the colors show that you get a lot of wintertime precipitation here in the Pacific Northwest. I used to live in Seattle, so I can attest to this. You also get a lot in the southeast US, where it's fairly dry here in the central part. Well, when you look at the model and see how it compares, here was our region of interest, the western US. It's really not too bad in the western US. I'll tell you in a minute about some disagreements, but it gets sort of the magnitude okay. The main error it seems to have is it's too spread out. You see it's too diffuse here. It's kind of smeared out a bit. And there's a specific reason for that, which I will tell you about now, which is we want to take this kind of global model. This is a model over the whole Earth, and we want to apply to our specific region. Well, when you get a model over the whole Earth, because the resolution isn't that fine, the grid points where you calculate quantities are fairly far apart, it tends to smear things out. So we take steps to try to correct that. That's called downscaling, focusing on our region of interest. So why do we want to downscale? Well, I just alluded to it, but here's our region of interest over the western United States. We're down here in San Diego. And see these orange dots? Those are the global model grid points. So the global model will predict what's going to happen at each one of those points. And we were particularly interested in water. Remember I said at the first, it's an arid region. We want to look at what happens to water resources. Well, here are some basins of rivers, important rivers in the US West. It's a little washed out, but this one here is the Columbia River Basin. This one here is the Colorado. And look what happens. There's about 6 global model grid points over the Columbia River Basin. So that's not too good. I mean, you can't tell that much with such poor spatial coverage of where you're really interested in. So what we do is we downscale. We take the global model results and we use a model embedded inside that has very high resolution on our region of interest. That's those green dots there. So we take the global, which is the orange, and put them on the green. Actually, we do that dynamically, so it includes all the physics on those green dots. So we get much better coverage over our region of interest. And again, like I said, we spend all this time validating. I don't think it's necessarily interesting for the general audience, but I'll just show you one, kind of an indulgence here. This is how the downscaled model simulates El Nino rainfall. I think probably everyone here is familiar with El Nino because it has great impacts in San Diego. Here's the observations of what El Nino does to precipitation. These blue colors means that you get a lot of extra rainfall in these places when you have an El Nino year. So you get a lot of extra rainfall in Northern California. You get some down here in Santa Barbara, Los Angeles Basin as well. On the other hand, it's drier up in the Pacific Northwest. That's an important point I'll come back to later on. Now here's the standard reanalysis, which is the global model grid. And what you see is immediately it's very washed out. You don't get the amplitude of the response. I don't know, maybe you get the sign of it. It's a bit wetter over California, but it's really not very satisfactory. And again, the reason that's happening is because the grid is just too coarse. You really want to focus in on your region of interest, and the global models can't do that yet, although they're working on it. So here's the downscaled model. I think you see that as considerably better than the global model. It gets that blob of excess precipitation in Northern California, gets some drying in the Pacific Northwest. So this is just one of the ways we try to verify the model before we use it. Say, does it seem to simulate what we actually see happening in reality? I'm going to jump right to the result here of the project. This is the change in California snowpack in November. The right-hand panel will show what happens in year 2050. The left-hand panel is current. And what you see is the height of this blob here shows how much snowpack you have in California now and in the future. And if you look, you see you get much less snowpack in California in the future. Here is March, and you see, look how much less it is. It's amazing. So I'm going to let that run through one more time. But one of the main results of the climate change part of this research was that California will have much less snowpack by the year 2050 on average. There's still a lot of year-to-year variability, but on average it'll be much less. And the reason why I think this matters to everyone here is because the way that the water system runs in California is it depends on the snow in winter to supply us water for the summer, for agriculture, for commercial purposes, for drinking. So this is a natural reservoir which holds water from when it comes in the winter up until late spring or summer where we really need it. If that goes away, we're going to be in trouble. And it's not we're in trouble because the absolute amount of water is less. I'll show you in a sec, but the actual amount of water isn't that different. What's happening is that because it's warmer in the winter, more of what was snow then falls as rain. That just falls onto the ground, goes in rivers, and is carried out to the oceans. So it's lost from the system. It's not retained in reservoirs because they let their gates open in winter generally so they can close them to prevent floods in spring. So this water is lost to the system, so it's going to be a problem if you don't compensate for these kind of changes. So now I'm going to show you, I mentioned a second ago that there's not actually that much difference in the amount of precipitation falling in California. That's shown in this right-hand panel here. Here's the difference in precipitation in percent between 2050 and today, according to this model calculation. And this zero line goes right through California. That says to the first approximation, there's not going to be much of any change in the total amount. What changes is the temperature. Here's the temperature. It's about 1 degree centigrade, which is about 2 degrees Fahrenheit, warmer by year 2050. So the precipitation more falls as rain instead of snow, plus it melts earlier in the spring. And that's what drives those changes in the snowpack. So as you can imagine from that, the rivers start flowing earlier in the year. This is just a graph showing the day in which half the water has gone down the river. This happens to be the Merced River in California, but we did it for other rivers as well. And right now, it's about mid-April, the day when half the water over the year has gone down the river, is in about mid-April. Now in the future, because that more of the rain is falling, more of the what was snow is falling as rain in the winter, plus it melts earlier, that's going to move earlier and earlier in the year. That'll get to about mid-March maybe, about a month earlier. So it's interesting to look at, again, observations. I keep mentioning this validation, but that's a very big issue for us. This isn't, again, this is another comparison to observations. This shows observed change in stream flow between 1948 and the year 2000. They go out to all these streams and they put meters in the streams and they actually measure how much water is flowing down those streams. And this shows the change in stream flow. At all these different streams, there is a dot for every stream they've measured over the western US. And a blue dot this size means that the flow is coming 20 days earlier compared to 1948. A red dot means it's coming later by 20 days. What you see is over the vast majority of the western US, streams are flowing earlier in the year. So that's exactly what you would expect from the model projection. So it's another way of validating the results. Well, what effect this has depends on where you live. So for example, in the Columbia Basin, they're forever arguing about, do we spend their water on hydropower or do we use it for salmon? To some degree, you can't have both, because when you retain the water for hydropower, it makes a very bad environment for the salmon. And there have been a number of lawsuits in the Pacific Northwest. And in fact, it's gotten to the point where some federal judges have said that you have to tear down some dams, which generate about 1 gigawatt of hydroelectric power, to have better flow for the salmon. So this is already a contentious issue, and it's just going to get more so. Now for us here in California, one of the effects it will have is on the Los Angeles water supply. The reason that makes a difference is because Los Angeles doesn't have much indigenous water supply. It imports a lot of it. So this shows the chance of having a shortage in the Los Angeles water supply. Right now you have about a 0.3 chance. And what that means is, any particular year you have some chance. That's not too bad. If you happen to have 1 year where it's a shortage, you just put in some restrictions on use and conserve some, and then probably next year you'll be okay. But what it shows is, here's the chances for year 2025, 2055, 2085. You see a large increase in the chance that you'll get a water shortage in Los Angeles. And again, 1 year isn't so bad. But if you start having multiple years of shortage in a row, that is very difficult to deal with. So when you've got these larger chances, it's much more likely you'll have multiple years in a row. Now one thing people often ask me about is, why do you get this change between these different decades? And that's actually fairly interesting. The real world amount of precipitation changes quite a bit from decade to decade. I'll show you another example of that in a second. But the models capture this real variability. So if, for example, you were to make a treaty with Mexico saying how much water we should give to Mexico, you might set it at a value that's very high, because you don't understand that that varies a lot from decade to decade. Well, this is exactly what happened. The amount of water that we're supposed to release to Mexico in the Colorado was set on the basis of flow in a decade that was unusually wet. Well, that's too bad, because what it actually should be is more like this. So even in regular times, it's rather unlikely that we'll meet that target. That has to then be made up in other ways, such as flow in the Rio Grande. But in future years, that's going to become even harder to hit. So there's implications for international treaties as well. We have a fellow here, Tony Westerling, who's looked at how this might affect wildfire. I know that, again, that affects everyone here. Now he has a model showing how wildfire responds to various environmental conditions. And this has been a great boon for people who try to fight wildfires. He now issues a forecast for the entire western US of what the probability of having wildfire in any particular location is. We asked him to use our results and run them through his model, and what he found was that the expected number of acres burned in his test plot in the Sierra Nevadas about doubles by year 2100. And the reason for that is twofold. Like I said, more of the precipitation falls as rain in the winter. So as you know, when you've got rain in the winter, that's when you get a lot of brush growth. And what really fuels these fires is when you have a lot of brush growth sitting around from the previous wet winter. And the second part is it's warmer and drier during the summer. So that just makes the conditions even more extreme for fire. There was a fellow as part of the Project Lance Vale at PNNL who looked at what effect this might have on salmon. Salmon live in this area here of the Pacific Northwest. Now, the way he tells me salmon work now is that they know to start swimming upstream when the water temperature drops. That's one of their indicators. And then, okay, so they swim upstream, they lay their eggs, the eggs hatch, the juveniles grow a little bit, and then the juveniles hopefully get large enough to survive the transit back downstream, and they know when to start swimming downstream when this burst of meltwater comes in the spring. So over eons, they've acclimated to this particular timing between when it gets cool in the fall and when there's a pulse of meltwater in the spring. Well, you can probably see where I'm going with this. In the future, it will stay warmer longer in the fall. Plus, I mentioned that it melts earlier in the spring. So the salmon, for example, will get pushed on both ends of that reproductive cycle. Now, it's the kind of thing where you can't say that any one particular salmon, makes it or doesn't make it because of this reason, but just as a population, it becomes harder to survive. We had a fellow here, Noah Knowles, who looked at what effect this would have on salinity of the San Francisco Bay. Now, I know this plot's a little hard to figure out. You're looking at this region here in California, the San Francisco Bay Area. The colors are water, not land. So here's San Francisco, here's San Jose, and Oakland's over here. So here's the bay. All this color is the bay water. And the colors show you how salty the water is. Now, what determines the saltiness of the water is how fast it gets flushed out by rivers. So the rivers flow in. Right now, you get this difference between practically fresh water here where the river lets out, and of course, pure salty ocean water out here in the ocean. And you get this region of transition and salinity between the two. So if you look at the colors, it shows the salinity. This is a measure of salinity. It's about 20 parts per thousand, which is about 2/3 of what ocean water is in this region here of the San Francisco Bay. But in the future, in the summer, the river flow during the summer, remember, it's going to happen more as winter, less during the summer, so there won't be as much flushing out. So the result is that you'll have more intrusion of this salty water up into the estuaries. Now, I'm not a biologist, but the biologists tell me that this is really pretty bad for the critters that live here because they're quite sensitive to the exact salinity of the water. So let me just summarize that. So the projections are for a reduction in winter snowpack is going to be the main effect. And this is made worse by air pollution. I didn't have time to get into that, but you've probably heard how, burning coal and, even cow dung from, say, Asia puts particles up into the atmosphere. They can fall on the snow and make the snow darker. Then it absorbs more heat and it melts more easily. So for various reasons, you get a reduction of winter snowpack. Plus, precipitation is more likely to fall as rain, and what snow there was melts earlier in the year. That's the main result, and what it means is that river flow comes more in the winter or spring than in the spring and summer. And that has all these implications I've mentioned for wildfires, agriculture, recreation, and how reservoirs are managed in California. That affects fish, whose life cycle depends on the timing of water, temperature, and spring melt. And it also affects the creatures who live in San Francisco Bay. Now that was sort of the background of why we decided to look at this. Now I'm going to carry it through and tell you what this says about energy. So I haven't talked about it up to now, but I hope it's pretty clear that this makes a difference to temperatures too. I mean, it's fairly self-evident. So what this graph shows is how often you get heat waves in the Southwest between 1870, which is the bottom here, and 2090. And these black dots are heat waves in the current time period, and the red dots are heat waves in the future. So if we start here in 1870 and go up to 1950, in the southwest you get these smattering of heat waves on any particular summer. And what this is showing is, look how you get more and more dots as you move up to the year 2100. What that's saying is you expect to have more and more heat waves. And the number of hot days per year, where hot is defined as greater than 95 degrees Fahrenheit, is shown in this bottom graph. You see you might go from 20 hot days a year to 60 over this particular region. We like showing this one to all the people that come down from Sacramento, our lawmakers. That's because it's the daily high temperatures in Sacramento. The blue curve shows what we get now. It shows how often you get warm temperatures of a particular degree. So for example, here's 90 degrees right here. So that blue shows how often you get temperatures of 90 degrees. Currently is the blue curve. And then in the future is the red curve. So what you see is that, for example, the most common hot day is 90 degrees. That actually doesn't change, which I thought was kind of interesting. What changes is this distribution gets shifted, so you have more warm days. For example, the number of days greater than 95 might go from 5 right now to 10 in the future. And the reason that we care about that is because on a warm summer afternoon, 40% of all electricity in California goes to air conditioning. I was surprised how much that was when I first heard that, but it's huge. So if you've got more days, the energy people use this rule of thumb. They say, if it's greater than 95 degrees, no one's going to hold back on their air conditioner. If they've got one, they'll turn it on. So that's why we use 95 degrees. So if the number of days with 95 degrees doubles, it could be quite an impact on the energy use in California. So that's what motivated us to start looking at these energy issues. So the overview specifically of the California Energy Project was we wanted to see, do our predictions have any economic value? I mean, that's a way of saying, can they take this information and put it to good use for planning purposes or otherwise, however they can use it to optimize their operations. So we wanted to determine the economic value of climate and weather forecasts to the energy sector. Well, as I said, climate and weather affect energy demand. You already know that. But this shows the temperature in California across the bottom here. And this is the energy demand that you get for different temperatures. So it's actually a minimum around 70 degrees Fahrenheit. If you go up to 100, it can go from 28,000 megawatts to 40,000 megawatts. So it's a very pronounced difference. And it's bad for the energy companies in the sense that they have to plan for reliability purposes to deal with a day like this, even if most days are like this. So it's inefficient and expensive if you've got a lot of capacity sitting around that's only used 1 or 2 days a year. So maybe if you could know something about the distribution of temperatures, you'd be able to plan better. Well, climate affects energy demand, but it also affects energy supply. So it affects both sides of the equation, supply and demand. What I'm showing here is this is the typical effects of El Nino on precipitation and temperature. And it's a little hard to see in the colors here, but it's warm in the upper Midwest during an El Nino, and that affects how much people use natural gas. So if you have an El Nino, people tend to use less natural gas in this region, and that actually makes a difference to our natural gas prices here in California. I mean, you'll notice this on your energy bill. Another way it affects us is that it tends to be dry during an El Nino in the Pacific Northwest. Well, we get about 10 to 12% of our hydropower from that region. So if we don't have that 10 to 12%, our energy costs tend to be higher. And that's because although it's only 10 to 12%, it tends to be that amount that's used for those swing days when it's really warm. So if you don't have that for those warm days, prices can really shoot up. And I'll show you some examples of that. So climate affects energy supply and demand. To look at this, we had a bit unusual project to look at it. You may not appreciate how unusual this is, not being in academia, but what we usually do is we just talk to other academics. So for example, here we are at the Scripps Institution of Oceanography. We worked with the University of Washington and Georgia Tech on this project. And frequently this kind of project would have stopped there, which is fine, nothing wrong with that. But we wanted to really bring this to people who actually made decisions about the real grid that's powering, say for example, these lights. So we partnered with people who make the rules that govern the energy grid and actually run the energy utilities. So we worked with the California Energy Commission, which has a big role in forecasting energy use in California. The California ISO, the independent systems operator, they're the people who actually run the grid all over California. So the electricity coming here right now is delivered to us by the ISO. Then we worked with utilities. Pacific Core, who I'll describe in a few minutes, we worked with San Diego Gas and Electric, people right here. We worked with SAIC, who have a lot of insight into the energy industry. So we try to make this integrated program where we actually talk to people who made decisions in the relevant fields. And we found out some interesting things. I mean, I've gone on and said, aren't these climate forecasts wonderful? And we found out, they don't actually use them. Well, that was a bit of a letdown, but the least we could do is try to figure out why they don't use them and perhaps try to address that. So the main reason that we found that the energy industry doesn't use climate forecasts is because they're probabilistic in nature. Okay, and what that means is that we don't say that next summer is going to be warm. We say there's an enhanced chance, and we can tell you what the enhancement is and how likely we are to be correct or wrong. Now, I think that's pretty usable information, and in fact, the insurance industry, that's all they use is probabilistic information. But the energy industry wasn't used to thinking this way. Let me show you an example. Here is the amount of rainfall you might get, say, in San Diego during an El Nino. Oh, sorry, this is during a regular year. So you've got, of course, the most likely thing is you have a normal amount of rainfall. Then you've got some chance of having a wet winter, some chance of having a dry winter. Now I'll put on the other case. This is the La Nina. When it's La Nina in San Diego, we tend to have dry conditions. So here's what the distribution of rainfall looks like for San Diego, just schematically, during a La Nina year. And so if the newspaper calls me up and says, well, there's going to be a La Nina, what does that mean for San Diego? I say, well, it tends to be dry. But that's a very glib answer, you see. That just means that this curve is shifted to the left, so you're more likely to get dry than you were before. Actually, you see, you've still got some chance of wet. And this happens all the time. We'll go from this curve to this curve, and it'll be wet. And people will be saying, well, the climate prediction was wrong. It's like, oh, okay. But actually, if we could somehow convey the full nature of the distribution, you would see there is some chance of that. As long as the probabilities aren't wrong, that's what you need to plan for. So it's all probabilistic when you're talking about climate forecasts. So it's hard to make this understood to a lot of the application users, especially when they're not used to thinking of it this way. Sometimes the language is hard to understand. So for example, let me go back to this. Let's say that this yellow curve, let's say I call that an average year. Let's say I call that an average year. Now what frequently happens is if I say I expect an average year, people will think we will not get wet, we will not get dry, we will only get normal. But that's not right. See, the average year has a third wet, a third dry, and a third normal. So you just get tripped up on terminology. You have to be very careful about these things. And really the last and maybe biggest thing is simply aversion to change. Okay, we found out that the energy industry has ways of doing things they don't want to change. And part of the reason is because it's probabilistic. It goes back to the first. If they do things the way they've always done, and it turns out to be different than they expected, they don't get blamed. It was how the guy did it before. But if they do it differently, and remember, you can get some chance of what you don't predict. If you get this wet year, when you expect on average dry, they feel like they'll get blamed for that, maybe fired, so they don't want to do that. So that was probably the biggest thing we faced. But let me show you some specific examples of what we have done for the energy industry and how they're trying to use this information. Now the first one is called the California Delta Breeze. And anyone here who's lived in Sacramento really knows all about this because that's where it happens. I'll show you a movie of it in a sec so you know what it is. But let me just say it's an important source of load forecast error, which means the Cal ISO, the people who bring us our electricity, they want to know a day in advance whether or not they're going to have a delta breeze because it makes a huge difference to how much electricity people use. A big delta breeze event can change the electricity use by 500 megawatts, which is about 1% of everything used in California. Now, if you think 1% in a sense doesn't sound like a lot, But if you think of these stage 1, stage 2, stage 3 alerts we have, I think those go off at about 5%, 2.5%, and 1% electricity supply. So if you get all of California wrong by 1% just from this one phenomenon, that's bad. So the direct cost of this energy is something like $250,000 for each breeze day, which is like $10 million a year, not peanuts. But I think actually the big cost is if you push a stress system that's really on the edge past the limit of its capacity. So the delta breeze makes things cooler. So if one dies, if it suddenly dies, you thought there was going to be a delta breeze tomorrow. So you think it's going to be cool, but it doesn't happen. So it's much warmer than you predict. So there's a lot more electricity use. You could have rolling blackouts. That's the real cost of this. Okay, this movie shows a no delta breeze condition. So you can see what it looks like. Here's the San Francisco Bay Area. San Francisco, Sacramento. This shows September 25th, 2002. Okay, there was no delta breeze this day. And hot air just came roaring down the Central Valley. I spent a couple years there. It's really kind of nasty. You get a lot of days over 110. You know, the air currents just bring this hot air. Like I said, if you have an air conditioner, you turn it on. The power consumption this day was quite high. Now I'm going to show you the very next day, September 26, 2002. So you see how totally different it is just in one day. So there's all this cool marine air coming in over California. And I'm going to zoom in here to show you something very interesting from our climate forecasting point of view, which is that the delta breeze is set by a lot of these very large scale conditions. But it flows in here through the San Francisco Bay Area, and see these hills right around the San Francisco Bay? They have a very strong effect in channeling the airflow into the Central Valley of California. And it's really hard to have a forecast which takes into account these huge scale, thousands of kilometers, plus these little tiny hills. I mean, here's Golden Gate Park. I mean, that's the scale we're talking about. So it's very hard to get forecasts of this correct. Well, we thought we'd take on that challenge. Here's what the regular weather forecast of the delta breeze looks like. This is the predicted wind speed along the x-axis here on the horizontal. Here's the actual wind speed on the vertical. So if we always got exactly what was predicted, these dots would fall on a line, on a straight line. So what you see is this scatter means that it's not being predicted well. You've got some prediction for what the wind speed is going to be, but that really doesn't tell you much what it's going to be. It's not very useful. So we developed a climate-based statistical forecast for the delta breeze. And I'm just going to show you one example. It's a little bit complicated, so let me walk you through it. This shows the chance of having a delta breeze under certain conditions starting at 10 a.m. this coming up day. And the reason we picked 10 a.m. is that's the time that the ISO, which brings us our power, starts their delta breeze day. You know, the power really starts to come on at 10 a.m. Well, they have a chance at 7 a.m. to make a last correction to the forecast to see if it was right or wrong. Well, at 7 a.m., we can tell them under certain conditions, there is only a 5% chance that you'll have a delta breeze this day. Now that's very useful for them, because remember how bad the dynamic forecast is? If the dynamic forecast says that there's going to be a delta breeze, but this says, well, historically, there's only a 5% chance you're going to have a delta breeze, then they can correct their forecast to take that into account. So this gives them a way of increasing the skill of their forecast. So just to summarize that, climate information can do better than dynamic weather forecasts under certain conditions. And the possible savings here are about 10 to 20% of the costs they incur due to weather forecast errors. You know, they have other sources of error, but this is one of them. And the amount of money we're talking about, it depends on the utility. I mean, so SDG&E is pretty small, you know, PG&E is larger. Anyway, it depends on the size of the utility, but the kind of numbers we're talking about are the low hundred thousands to the millions of dollars per year. So the second example I'm going to talk about, we did in association with SDG&E right here in San Diego. And it's called load demand management. And what they want to try to do is induce customers to reduce the electrical load on those days that have the highest load of the year. And I'll show you in a sec why you want to do that, but from our point of view, the prediction challenge was to call the 12 days with the highest electricity use 3 days in advance. And what they actually do is they get on the phone and call their customers, say, please don't use electricity this year. Not you guys in the audience, but industrial customers who have signed up to get reduced rates by adhering to this program. So why do you do this? Why do you shave peak days? Well, this is the price of electricity in California over one particular July in 2000. And look what happens. Okay, here it is idling along at $50 a megawatt hour. Boom, goes up to $500 a megawatt hour. Overnight, literally. And that's because it was much warmer these days. So it'd be like if you go to the gas station, all of a sudden gas is $20 a gallon, when you're driving home, and it takes $350 to fill up your tank. I mean, it really blows your budget. So, these are very difficult for the utilities to handle. Here's another way of looking at that. Here's the demand in California, and here's the price. And you see, you just hit this wall. When you have a little bit more demand, the price just shoots up. And that's because once you reach here, there is no more electricity to be had. You simply can't get it. So the price just shoots way up. So what we try to do is move days from this part of the curve just a little bit less. They only need a little bit less to really drop the price. So here's a typical July. I'm going to show you how we evaluate this kind of thing. Here's a typical July. What's shown on here is the amount of electricity use and the temperature on each day in July. And the average electricity use is 2916 megawatts. And here are the top 3 days. The top 3 days use 3,383 megawatts. So the top 3 days use 16% more than average. Okay, so that's how we're going to evaluate it. If you knew the electrical loads in advance, the top days use 16% more than the average summer day. Now it turns out that the PUC, who regulate the utilities, have certain rules. You can't call more than 2 events of these peak day events per week. They just don't let you. Well, that's too bad because we know heat waves happen in multiple days in a row. But you can't call them, so you can only call 2 days in a row. So that reduces the potential you have to 14. That's the best you can do, given the governmental constraints. So let me show you warm days. Here are warm days in this hypothetical July. And what you see is that some warm days correspond to the peak use stage. But there's one warm day that didn't happen to be a peak use day, maybe because it was Friday and people left early. Okay, so on warm days, on average, use 11% more electricity than the average day. So we go from 16% more if you knew electricity. If you knew temperature, because you don't get the exact days correctly, and you can't, just with temperature, you can only get 11% better than the average day. This represents how much electricity you save. Well, what can climate forecasting say about this? This is actually temperature at Miramar, so not too far from here. And this is on a tariff day. It tends to be very warm in Miramar. You're not surprised because that's an important area in San Diego County. And look, it's warm plus getting warmer on a tariff day. I should say on one of these days when you have peak electricity use. So that's kind of straightforward, right? When you have these days of high use, before them it's warm and getting warmer. Well, that suggests a way of predicting them. Just say if it's this warm and getting warmer, we'll just forecast the day. See, that's how simple it is. It's really straightforward. How's that do? Well, with a fairly conservative number of 24 degrees centigrade and half a degree warmer than the previous day, the days you pick are about 6% warmer than the average. So this is what you get with this incredibly simple-minded scheme. I actually call it the super simple scheme. If you had a crystal ball that told you the temperatures, you could only get 11%. So that's really not so bad. And in fact, I've been pretty conservative here, but we let the utility be as conservative or wild as they want. I mean, it's up to them. So this rather complicated figure lets them pick how they want to run their forecast. And the way it works is they look at the temperature along the x-axis. This would be the temperature at Miramar. And along the vertical axis is how much warmer it was than the previous day. So I showed you when it was 24 degrees centigrade at Miramar, plus this amount warmer than the previous day, gives you about 6% more electricity use than average. But they could push it way over here to 7.5%. The problem is you start running out of days. They want to call 12 per year. And you can imagine if you waited till it was 115, you would never get days like that. So you start running out of days. You can't make the criterion too sharp. You run out of days. But they can pick that themselves. They can make the trade-off. So they can use this to help call these days in advance and make their system more efficient. So what are the economic value of this? Well, ultimately, your electricity meter might have a little light on it that says, don't use electricity right now unless you want to pay a lot more. And that's what they're talking about doing. But you know, that's some years down the line. You have to go out to everyone's house and put in these meters, so that's expensive. If you did that, you would save, just in San Diego, about $12 million per year. Well, until then, the climate prediction is very easy. I mean, you saw how simple it was. You don't have to go out to everyone's house and put in a meter. Well, that gives you about $1.3 million a year. So the climate analysis gives you the expected benefits, plus it gives you a way to start them. It starts getting people used to doing this, plus it gives them some benefit right away. So the third example I'm going to show is irrigation pumps. I didn't know this when I started the project, but irrigation pumps, you know, that farmers use to irrigate their crops, are a very heavy electricity load in the western US. And we worked with PacifiCorp, a utility that operates in these blue shaded areas. We focused here on southeastern Idaho, but they wanted to know when the farmers would start turning on their pumps in the spring. Okay, and they had no idea. They didn't know when the farmers would start to turn on their pumps, and we said, well, heck, let's look at that because it must be related to rainfall somehow. So this shows the day of year. Okay, this is like April, May, June. And this shows the electricity load in southeastern Idaho. And you see, when they turn the pumps on, boom, you get a peak, and it goes way up in summer where they're irrigating like crazy. Okay, and they asked us to call in advance these days when they reach 20% of the load. And let me just show you a different year, because you can see it can vary from year to year. This year had the day right here. It was a month earlier in the red curve, so it varies by about a month. So here's the day when the pumps started over time from 1997 to 2003, and these blue dots show what actually happened. Now we looked at predicting this, and here's what we came up with. This is actually using, now I want to be careful here, we use the simultaneous rainfall. So this is when in spring the pumps turned on, and to get the prediction, which is the red curve, we use the rainfall in spring. So we use the rainfall at the same time. Now it turns out the rainfall at the same time gives you an excellent curve fit here, but it's not useful for prediction because that doesn't tell you in advance. So that's useless from their point of view. You can't use it until it's already happened. So we went back to them and said, well, we can explain it, but we can't predict it. And they said, well, you know, actually, we didn't really want you to do that. And we said, what do you mean? And they said, well, what we really want to know is total use over the summer. And the reason we asked you to do this first one is because that indicates total use over the summer. So after rolling our eyes a bit, you know, we asked them to give us the total use over the summer, and we look and see if we can predict that instead of going through this intermediary. And we found something very interesting. Here's the total electricity use over the summer on the vertical axis, and these dots show various years. And on the horizontal axis shows how wet or dry the soil is in spring. So this is use of electricity over the summer on soil moisture in spring. So this is a true prediction that they can use. And what you see is that when the soil is very dry in the spring, they tend to have a lot of total pump use over the year. When it's wet in the spring, they don't. So they can use this for prediction. So the irrigation load summary is that they found that they can buy power contracts 2 months in ahead. Now, if they know that the load is going to be high in the summer, they can save $25 per megawatt hour over the spot market price. So if they buy in advance on contract, they save rather than waiting till the last minute. They use about 100,000 megawatt hours. That gives them a savings of about $2.5 million per year. So it's fairly useful to them. So the fourth example I'm going to show is how the North Pacific Oscillation affects California. And I don't know if you've heard of the North Pacific Oscillation. It's not nearly as well known as El Nino, but here's a picture of it, okay? So here it is in what we call the high phase. And in the high phase, these colors show the temperature of the ocean surface. These red colors show that it's warmer along California in the high phase, and it's cooler along California in the low phase. And one interesting thing about the North Pacific Oscillation is it tends to vary rather slowly. So here is the variation of this over the past 100 years. And you see it goes in these slow cycles. So what we can do is we can say, although we don't have a good dynamical way of predicting what it's going to be, it gives a fairly good, useful prediction rule of thumb to say it won't change much from the previous time period. That's borne out by history. Now this affects California. This affects everyone here. And the reason is as follows. When you have an MPO, a North Pacific Oscillation in a particular phase, this shows what the air surfaces look like up in the atmosphere. And you know when you have high pressure, you literally have a lump or a hill of air sitting up in the atmosphere. There's higher pressure up in the atmosphere. So under these conditions, you have a hill of air up in the atmosphere, sort of over the north central Pacific. And air tends to try to go downhill, but Coriolis turns it to the right, which means it brings Canadian air down over the northwest part of the United States. So it's bringing all this cold air down over California. So our winters are colder. It's as straightforward as that. When the MPO is in this phase, our winters are colder. We use more natural gas to heat our homes and businesses. Well, how much? About $250 million. It's really fairly significant. The phase of the MPO makes a $220 million per year difference in natural gas use depending on its phase. That's just in California. Be a lot more over the whole western US. And I just want to mention the MPO affects the summer too. I'm going to show how it does that. So this diagram is way too busy, so I'm just going to focus here on San Diego where we live. So this is saying when the North Pacific Oscillation is above normal in the spring, so again we're thinking of prediction. We're going to start with spring and look at summer. When it's above normal in the spring, you have a 59% chance of having above normal temperatures in the summer in San Diego. Only a 12% chance of below normal. So it makes a pretty big difference to everyone who lives here. So the benefits of this are better planning, because you know a few months in advance what you expect. Perhaps these long-term contracts versus waiting till last minute to buy a spot market. And the last example I'm going to show is hydropower. Like I mentioned at the beginning, El Nino affects precipitation, and that affects hydropower. So this was Cal Energy work done by our colleagues at the University of Washington. And what they wanted to know was, can we predict hydropower variation in California in the Pacific Northwest? Because if we could, we'd be able to say something about that source of energy. Well, the first thing you do if you want to say that is you have to know what the precipitation was over history. So they developed these historical precipitation fields. This is just one example. I think it's interesting that it shows you the kind of scale you're looking at. You get huge effects from the mountains. You really have to take that into account. So you develop these precipitation fields, and then you just let them fall on a model that models where rain goes when it falls, quite literally. And they look kind of like this. It's rather abstract, but all these little lines show where water runs to when it falls on the ground. So these turn into major rivers. So for example, starting here, here's the Bay Area around San Francisco right there. You can trace it upstream. So this branch right here, that's the American River. There's Sacramento right there. So this mimics what's actually happening in California, all the stream flow in California, where the water goes. I'm not going to read this to you, it's way too dense, obviously. I just want to give you a feeling for what it includes. I'm kind of amazed that they included all this stuff. So here's Lake Oroville. This is just one of the reservoirs. For example, it includes purposes, it's run for all these different purposes. Flood control, water supply, hydropower, water quality, environmental conservation. It's run by the DWR. I mean, this model of California's reservoirs has all these different components, you know, modeled down to what each one's used for and who runs it. It's incredible. So finally, you make hydropower out of that. You've got an amount of water in a reservoir. You just let it run through the turbines and make hydropower. So this shows the amount of hydropower from 1951 to 1994 at Shasta in megawatts. And it's actually, this is typical. You see a lot of changes year to year, like I mentioned before. There's a lot of variability depending on decades. You see kind of a trend towards less. That may be that more meltwater in the winter that I mentioned before. So we're looking into predicting this kind of variability. So what are the economic values? Just to summarize all these different applications, we started with the improved Bay Area and Delta breeze forecasts That's in the hundred thousands to the low millions dollars per year. Peak day load management, that's right here in San Diego, our own backyard. That could save $1 to $10 million per year, just to start with. Pump loads, just in Idaho, of course, obviously there's a lot more pumping than Idaho, but just in that one region, knowing those in advance can save you $2 million per year. If you know Pacific SSTs, which we do, benefits of that information telling you what's going to happen in the winter or summer might include risk reduction. You can operate the grid better, improved reliability, or improved planning. And finally, when you have hydropower predictions, you can do a better job of water management and reduce costs. So, thank you for your time.